Okay. Okay, so good evening everyone and welcome to the 8th live session for the course Basic Real Analysis. So today the problems what we'll be discussing are based on integrability, okay, integrability of functions. To begin with, let's start with this question. So this we have to consider this function. Consider the function f defined on 0 1 by f of x equal x square, sorry, when x belongs to 0 1 intersection q and it is x, okay, I think I've written wrong, x square if x belongs to 0 1 intersection q complement. Okay, so you have to check integrability of f. Okay, so integrability means Riemann integrability. Okay, so for this what we'll do is we'll partition the interval 0 1, okay, and then we'll try to see what is the upper Darboux sum and lower sum in that for that partition, and then we'll try to conclude something. Okay, so we'll choose the standard partition, okay, which is 0, which is the first point, x1 and so on, and at n it will be 1. So here basically xk is given by k by n. So there is uniform gap of 1 by n between each 2 points. Okay, so now for this we'll try to define LFPN and we'll try to find what is UFPN. Okay, if it is integrable, then the limit of both the things should be same. Okay, and in that case, when the limit is same, we say that the function is integrable. Okay, so we'll first look at this term. So by what is the definition? Definition is simply that k from 0 to n minus 1 will take the infimum over xk to xk plus 1 of the function f, and then we'll multiply by the length of that partition of the interval xk plus 1 minus xk. So this is what this lower sum means for this partition. Okay, now the question is, and similarly for UFP we'll try to calculate the supremum of the function in that partition, in each of the partitions, in each of the sub intervals, and then we'll try to see what it. Okay, so this is supremum. So now the thing is that the function is of this kind. So at each rational point it is taking the value x, and at irrational it is taking the value x square. Okay, so before going to the infimum and supremum, let us look at this property that we know that when x is less than 1, then we know that if I take the power of x, then it will be less than x. Okay, so if we talk on this interval xk to xk plus 1, okay, the supremum is always going to be achieved by the value at the end point. So see, there are two cases. So supremum will be what? So case 1, when xk plus 1, okay, so this function we know it's increasing, right? This function, so if I restrict each of the function, okay, we know that, so or maybe you can define it in this way. So define f1x to be x for in 0 1, and f2x as x square in 0 1. Okay, then we know this function f is just restriction of this f1 and f2 on the rationals and irrationals respectively. Okay, so what we'll do is, we know that both the functions are increasing, so the maxima is always going to achieved at the end point. If xk plus 1 is rational, okay, if this is rational, then we know that this value is always greater than the x square thing. So if it is rational, then clearly the supremum would be xk plus 1. Now when it's irrational, we know that we can find a sequence, right, which converges to this irrational number. So what I mean is, so there will be two cases. So if xk plus 1 belong to the rational thing, then we know the supremum will be of f on that interval would be simply xk plus 1. And the case when xk plus 1 is irrational, okay, then I know there exists a sequence in that subinterval which will converge to xk plus 1. So we'll choose a sequence yk which will converge to xk plus 1. Okay, so yk are in rationals, q yk, and this converges to xk plus 1. And now we know this yk, if we restrict on this yk, I mean this interval xk to yk, okay, so let me denote it by some other thing, yl, let's say. Okay, so for each l, this xk yl will, I mean the maximum will be achieved at this yl by the same logic, because now yl is rational. And now we know that when this yl converges to this, the supremum of this interval, when it get enlarged, it will converge to the value of this yl, right, where the limit goes. So now since yl goes to this, so therefore supremum, again, if you calculate on this interval xk to xk plus 1, will be achieved at yl in each of the subintervals, and that yl is converging to xk plus 1. For on this yl, xk to yl, I know that the supremum value would be where is it? So supremum yl would be yl, okay, and then just a second. So here the supremum is xk plus 1. Yeah, so in this case, now this yl is this is the supremum value is equal to yl on this subinterval, and we know that yl converges to xk plus 1. So as l goes to infinity, so the supremum value will also converge to xk plus 1. So this would be again xk plus 1. So the supremum in any case, if you look at this subinterval, will be xk plus 1. Okay, so that's why, okay, so I said it for supremum. Similarly, infimum will be achieved at this xk, okay, by the same logic. And the infimum would be the square thing, because we know x square is always less than x. Okay, so the infimum would be, so I'll just simply write it. So the infimum would be xk square, and then you have this. Now we know that this gap is 1 by n. We have this uniform gap, and xk, I also know the value is k by n. Or let me first write this, xk square and then 1 by n, and I know that xk is k square by n square, and then you have 1 by n. So this is 1 by n cube, and what is the summation? So summation of k square, right? So summation of k square, when k is from 1 to n, you know it is n into n plus 1 into 2n plus 1 by 6. So similarly, if we substitute, so this is from 1 to n minus 1, this is 1 to n minus 1 k square. So this would be simply 1 by n cube, so would be n minus 1 into n into 2n minus 2 plus 1, which is 2n minus 1 upon 6. And so this would be nothing but 1 by 6, and then you have 2n square plus 1, and then minus 2n minus n minus 3n plus 1 by n square, right? So now you can clearly see that this will go to, if I take the limit, I know this term will go to 2. So this will be, so limit n going to infinity LFPN will be equal to, sorry, 1 by 3. Okay, now similarly we can do for the supremum part. Okay, so we will just try to see what comes up here. So this is k, so this is 0 to n minus 1. Supremum, as I told you, it will be xk plus 1. Sorry, this is k plus 1 upon n and into 1 by n. So this is nothing but, so 1 by n square I can take out, and then you have summation k plus 1. So this is 1 to n summation k, right? And this I know, this is nothing but 1 by n square n into n plus 1 by 2. So this is, so 1 by 2, and then you have 1 n cancels with this, 1 plus 1 by n. So this converges to half. So now since both the limits are not the same, so in this case what we have is that the function given to us is not Riemann integrable.
Sir,
yeah.
Sir, if xk plus 1 is irrational, then what is the maximum, sir?
Yeah, so okay, let me tell you again. So I am just concentrating, let's concentrate on this xk plus 1. Okay, now when xk plus 1 is rational, then I know the function here is increasing. Okay, so if whatever we have, this function, okay, is increasing function. I mean, okay, so let's not go into, so I know f1 and f2 are increasing. Okay, so if I look at, so when we have this xk plus 1, then I know f at xk plus 1 is equal to xk plus 1, and this would be supremum because we know that in this interval this is the highest value. I mean, this is what one function can achieve from this relation. Okay, this is one of the relation, and the second relation is that f1 x equal to x is increasing. So
sir, when x is irrational, you have defined x square, sir, value of the function.
Okay, then maybe I said it's x. So this is what I'm saying, right? So I'm saying when xk plus 1 is rational.
Xk plus 1 is irrational. At xk
oh, no,
plus 1,
I'm
the
saying
value
that
of
first I'm saying that when xk plus 1 is rational, then this is clear.
Okay, sir.
I'm explaining both the things. So when xk plus 1 is rational, in that case this is clear. So we have used this fact that f1 x equal to x is increasing, and the fact that x square is less than x. Okay, using these two facts we can conclude this. Now the thing is, when you choose xk plus 1 to be irrational, okay, now I can get a sequence yn here. So yn belong to, let's say xk plus 1 intersect with q, okay, such that this yn converges to xk plus 1. This I can get. Now, yeah, now I can write yn or yl if you want, yl. Okay, now just concentrate, this is some, let's say yl. Okay, now by the same logic I know that if I take supremum of the function on xk to yl, okay, of this, the supremum would be fyl, right? The same logic what I said above using this, and this is equal to yl. So the supremum in this interval is attained at this point, and the value is this one. Now as L goes to infinity, this point is converging to xk plus 1. Okay, so what I'm saying is that the supremum, you can actually prove that the supremum of f on xk to xk plus 1, okay, will be achieved by this limit of yl, okay, and which is equal to xk plus 1. Okay.
Sir, we can also see it by the graph, sir.
It's difficult to, I mean, get a graph, right? Because it's rational,
So
irrational.
if we draw the graph of x and x square separately, then we can compare both of them.
But in this
X
case,
is
the
line
supremum,
passing. Yes.
in this case, no, there is a difference. In this case, the supremum is achieved at the point, but here the supremum is not achieved. I mean, or yeah, it's achieved also. Why? Because no, it's not achieved, right? Because f at xk plus 1 is what? It's xk plus 1 square, right? So in
Yes,
this
sir.
case, supremum is not achieved.
Sir, but the points are, sir, rational, sir. Xk plus ones are all rational, sir.
No, no. YL are
You
rationals.
have taken the partition as, sir, 2, 1 by 3. So all
Oh,
are,
okay, okay. So yeah, you
we
are
don't
correct.
need to, sir.
Yeah, yeah,
But this
actually
is,
you are
sir, good,
correct.
sir.
Yeah, yeah, yeah,
Yes.
yeah, yeah. You are right. Because the way we have constructed is always rational. Correct. So we don't even
Yes.
need this kind of argument. You're true. Correct. Here xk's are always rationals. True, true. Okay. Then it's much more simpler. Like you
Sir,
can.
don't rub it.
Sorry.
So don't rub it, sir.
Oh, okay. So maybe I'll just squeeze it a bit. Uh, okay, so now let's go to the uh, but one thing. Okay, but in this case, like you'll have to use this argument. Okay, sorry. So what I'm saying that okay, this for supremum we don't have to think. Okay, this is not required for the supremum part, but for the infimum, because you see the infimum is achieved at irrationals kind of, right? So this argument would be actually needed for in this case. So how should I write? So this is how should I write? Or maybe let me convert it into infimum, because that's for supremum, as you said, we don't need this kind of argument because it's immediate. The way we have created the partition, the points are always the nodal points are always going to be rational, so we don't need this argument. But for infimum, you need this. So what can I say is so let me, if you want, I should write it. But everything will change to xk. Okay, I'll just write. So it will take a minute. So let me say xk belong to q complement. In this case, f xk would be xk square. Okay, so yeah, this is what we are using. And over here the second case would be that xk belong to rational. Okay, and in this case we'll take a sequence while converging to xk, and then the infimum would be achieved at f of yl. So yl is a sequence in irrational. F of yl would be yl square, and the infimum of f over this would be limit of yl, which is x yl square, sorry, and this would be xk plus 1 square. So the so the infimum, of f over xk to xk plus 1 is always going to be xk square. So here it would be xk square. Okay, so this would be needed for this case, the first one. Okay, let me then copy it, cut it from here. Okay. So this is not good. Cut this off. Okay, so let's move to the next problem. So I hope this is clear.
Yes, sir.
Okay. Okay, so let's go to what is the next one? Okay, so we'll again consider this Thome function. So f01 to r given by f of x equal to 0 if x belongs to 0 1 intersection q complement. Okay, and you take 0 as well in this, and then 1 by q if x is equal to p by q, where p q gcd is 1. Okay, and p q belong to natural numbers. Okay, so now the question is that again you have to check the integrability of f. Okay, so like before, we'll try to proceed in the same manner. So what we'll do is, so we know this theorem that if a function is integrable, then the upper Darboux sum, and so there exists a partition. So this is the, so if, suppose ab to r is integrable if and only if for all epsilon greater than 0 there exists a partition p such that ufp minus lfp is less than epsilon. So the upper sum and lower sum can be made arbitrarily close, right? So this is what we know. So we'll try to use this formulation to conclude that this function is integrable. Okay. Okay, so let us try to see what is this ufp minus lfp for this one. Okay, so so let's say I'll use this kind of notation just to denote supremum of f over xk to xk plus 1. Okay, and mk I'll denote by infimum over this xk plus 1 of f. Okay, so now, so I'll try to see what is, so let p be any partition. So 0 x0 x1 and xn is 1. So here I am not specifying what, because that how these xn's are, we are just considering any partition, and then we'll try to see how can we get a partition for which this difference would be less than any epsilon. So for that, let us choose any epsilon as well beforehand. So let epsilon greater than 0 be any number. Okay, so let us try to see what is ufp minus lfp. Okay, so this is nothing but you will take summation k is from 0 to n minus 1, this mk times xk plus 1 minus xk, and then you have this term as well. So this would be the final term, right? Okay, so now you can clearly see that the lower sum, this one, is always going to be 0, right? Because whatever partition I choose, I know that there are irrational number and the function is strictly greater than equal to 0, right? So f is, so if I know that it's greater than equal to 0 and I know that there are irrational in this interval, so the minimum is always going to be 0. Okay, and supremum is going to be achieved at some rationals. That's it. So this I can eliminate as of now itself. So this would be just, I'll just rub this off. So this is mk and then you have this thing. Okay, now so I know that this will be of the form 1 by qk, something like this, right? Okay, so now I have to make sure that this whole quantity is very small. Okay, so that can be made possible if I can say that this is very small, then I can conclude this is one way. So like there are two ways of saying that this whole quantity is small. So if I say that, what would be the simplest case, that I know that this is anyway bounded by b minus a, I know this. So if I can say that this is very small, let's say epsilon by b minus a, then I can conclude this is less than epsilon. Or no, I cannot directly, but okay, so by something. So here let's not say this is less than equal to, suppose mk is bounded by this kind of quantity. Okay, then this is epsilon b minus a, and now the summation would give me b minus a, so this would be epsilon. So once I can make this small, then I know that this will be small. This is one case. The other chance could be, okay, this is the what we should think of, that we should like to make this quantity very small. Okay, that should be our first goal. Okay, so then let's go to think like how can we make this quantity small. Okay, so now as I told you that mk would be of the form 1 by qk, where qk belong to some natural number, right? This should be the form. Okay, so now let us look at this kind of quantity. So suppose, so we know that 1 by q, so for q belonging to this natural number, I know this 1 by q will be less than some very small quantity. So let's say I'll make this less than delta. So this is possible if and only if I can say that q is, when can you, so q is greater than 1 by delta. Am I right? Correct. So this is possible that I want this quantity can be made be small, or can be made less than delta if q is greater than equal to 1 by delta. That means, so this is one thing, and when this will be greater than, so my goal is to make this very small. Now what if it is greater than this quantity? So this will be greater than delta if and only if q is less than 1 by delta. Okay, so what we see from here is that this quantity will be large. So this is some fixed number, right? So delta I am fixing at first. Okay, so when I am fixing delta, this is something which is fixed. So this is saying that this 1 by q will be greater than that fixed quantity if your q is less than 1 by delta. That means you get an upper bound for such q, and q is always greater than equal to 1, right? And q, I know that it is natural number, so it is always greater than equal to 1. So this tells you that this thing is possible for finite number of q's. Correct? So here let me write it precisely what it is. So I am saying that let delta, so choose delta, we'll make sure what delta is will later on, but as of now let's say choose delta greater than 0. I will choose what delta is. Okay, then I have this relation, right? Then I have this thing. Then 1 by q, this is if and only if this implies that is q has finite many choices. Now see, this is the functional value. So this is kind of, this is f at p by q, right? So now this q, I know that this has finite many choices, but what about p? Can you say, what can we say about
P is always one. P is always one.
No. How can you say
When
that?
sir x
No,
belongs to closed interval 0 1, then p is always 1 sir.
no. This 2 by
No sir, no
3,
sir. No, no.
2 by 3 is also.
Yes sir, it is okay sir.
So it just says that P by Q, I know it is less than equal to 1. This says that P is less than equal to Q. So now since Q has finite many choices, P also has finite many choices. So this implies that P has finite many choices as well. Because P by Q is less than equal to 1. Okay? Fine. So what we got is that, so we can say that there are finite many, so we'll name it. Okay, so let's name it as let's say q1 or q naught with a set, okay, where xk or xk or xl is equal to pl by ql, okay, belonging to 0 1, open 0 1, let's say. Okay, here also I should say open 0 1 probably. Okay, I have already mentioned. Fine. So xl by, yeah.
Sir, if we consider the sequence 1 by n sir,
One by,
then it always converges to 0.
correct.
Sir, from there we can also say this
So we are
thing, na,
saying
sir.
the same thing, right?
Yes sir, I think this is kind of APR sir.
APR means,
Archimedean property sir.
okay, okay, yeah, yeah, correct, correct. So what I'm saying, I'm starting with a goal that what I want is I want to make this small. So at what are the possibility that it will be large, and that possibilities are finite. That's what I'm saying, and it's from the here only. This going to 0, it's same as saying that 1 by n I can make it less than epsilon for most of the epsilons.
There exists M.
Correct, correct, correct.
Yes, yes.
So it's the same argument. So I think that also, I think, okay, so that would be better to write probably. But I don't want to deal with the sequences, that's it. Anyway,
Yes sir, this is fine sir.
correct. Okay. So, so this is what we have. So I define this Q naught such that this 1 by QL is greater than delta. Okay, so this is finite. So QL greater than delta. So this is, so let's say I'm naming it as x1, enumerating it x2. So let's say there are n points for which this is happening. Okay, fine. Now for the rest of the points, I know that, so I have to partition, I have to find a partition. So P was given to us. Okay, so okay, let's not name it as of now. We'll rename it now probably. So let P be any partition. Okay, then it would be bad way to write. I cannot write this x. So, but this is in this.
Sir, Z1, Z2, Zk sir.
Okay, let's. So actually, initially, I don't want to start with a partition, because partition now I'm going to define how I'll choose my partition. But anyway, let's say P be any partition, the general partition.
Sir, you can take refinement sir.
Yeah, exactly. So that I'll have to write it again. Okay, anyway. So let's say this is, then let's say this is something YL. This is Y1. Y2 and Yn. Okay, so we have these many numbers. So suppose this is 0 1. Okay, I'm just naming it as Y1, Y2, Y3 till Yn, let's say anything like this. Okay, so for these many points we have to take care. For the rest of the points, okay, so now the thing would be, so now let's say I'm defining another P star, let's say, this is Q0, let's say I am defining Q1. So q1 uh, q1 be any partitions other than these points. So let's say q1 is equal to some z1 z2, in this way let's say z1 less than z2. Okay, here also I am arranging it in this way. Let me write in as a set I cannot. Okay, anyway, yeah, as a set I cannot write. So here I am putting the condition that yk less than yk plus 1. Okay, similarly this q, so here I am defining it as a partition, not as a set. Okay, so q is like z0 z or z1 till z. So let's say this is some k, this is zl. Okay, so I have this 2. Now I'll take my q as q0 union q1. Okay, so this is my partition. Okay, so this is partition of this 0 1. Okay, and this zk is not equal to any of this yk. Zk is not equal to any of zl is not equal to any of yk. Zi not equal to yj. Okay. Okay, so now this is a partition of this 0 1 interval. Okay. Okay, but so I'll choose some other partition. Okay, so anyway I'll start with this, then I'll refine it further. Okay, so now let us try to see what is u f at q. Okay, if I try to calculate this one, so I'll have this q1, so u f q1 just a second. So suppose this is, how should I write it? So uf at q, let me write it this way. Okay, so okay, or let me do the partition now itself. Okay, so let me do it this way. So suppose this, I am defining another q naught tilde. Okay, q naught tilde is what? So now I'll not choose this y1. Okay, so see what will happen. So I'll just write roughly to make you understand first. So if I calculate this kind of thing, so I'll have this supremum of f on each of the sub intervals, and then I'll have this length of the interval, whatever ik whatever I have. Now I'll split it into two parts. One will be the supremum of f. So let's say on q0. Okay, as of now let's focus on this q0 and q1, and this would be q1. Okay, supremum of f and then length of ik, here also length of ik. Okay. Now you see here this supremum on this interval. So what is the value? I know that the value would be 1 by qk for some k, right? But I know that this supremum is not going to achieve. So let's say that, so I'll choose some small neighborhood around this. Okay, and my these zk's are away from these neighborhoods. Okay, so zk, suppose z0 is here, z1 is here, whatever you choose. Okay, it's not intersecting with these partitions. I'll tell you about the partition, I mean this sub interval later on. So this is kind of zl minus 1. Let's say this is zl. I'm just taking a typical case. Now on this interval I know that supremum will be achieved at some of the rationals point, and at those rational point I know that in this case, so this over here I know that whatever the value supremum if I take on this zk to zk plus 1, okay, this is going to be some 1 by qk, and I know that the rationals what I am getting here is always going to be less than delta. This is how we have defined this, right? Q0 are the collection of those points where rationals are taking, I mean where the rational is greater than delta. These are the rational point where the value is greater than delta. So at the rest of the point, I know that whatever so the value I am getting 1 by qk, this is always going to be less than delta. This is how we have defined this q1. Okay. So here I'll do a bit change over here in writing, but still. So this I know that this is less than delta always, and this whatever sum I'll get, this is b minus a, less than b minus a, right? This I can ultimately do. Fine. So this I can make it less than epsilon by 2. Now let's focus on this one. In this case, I know that the supremum value, I cannot use that fact that the supremum is small, so this whole summation is small. I cannot use that. Okay. So what I'll use that. So supremum I know f is given to be bounded, right? So this function f is anyway bounded function, the way it has been defined. So this function is always going to be less than equal to 1. So let's forget about this one. So what I am left out with, this is bounded by q0 L of ik. Now see this ik, I mean the interval are y1, y2. Now this distance can be very large. This distance can be very large. So that's a problem for us. Okay. So what I'll do is now, so instead of choosing this y1, y2, I'll define new kind of new way. So what I know that these are the y1, y2 points. So now the partition would be like this way. So over here, so z1, z0 are given there. Now here I'll define, how should I name it? So let's say this is, sorry. So let's say this is W1, this is W2, this is W3, this is W4, and so for each I'll define 2, W5, W6, okay, and this would be some Wm or Wm minus 1, Wm, and this length would be, so let's say I'm naming it as delta m. This length is so delta 6, delta 4, what I'm doing, okay, so I'm assigning each of them by some delta, so there's some problem in naming, just a second.
Sir, sir, you should have first proved this thing, sir.
Which
that
one?
If y1, y2, y3, yk are some points in closed interval AB, then we can find we can enclose these points in small subintervals.
No, this
Which
we
we
can always do, right? Because these are discrete points on 0, 1. Okay.
Yes, sir.
If it is the end point, so it's not that I'm saying that whenever its end point, we'll take that as the point. Like we don't need
So,
this
sir,
kind of partition.
so what is the need to prove this, sir? We can simply say that these subintervals are length of these subintervals can be made very small, sir.
Exactly. So I'm choosing each of the subinterval to be some precise value, and that would be constant. So maybe you can choose. So suppose, how should I say? So suppose these are total m number of partitions, right? So I'll choose this as delta by m. Suppose each of the partition has size delta by m. This I can do, right? So I don't need to prove these things. This is how I'm constructing it, right?
Sir, you should write it in terms of epsilon, sir.
Epsilon will come later on. So here I have not written what delta is, right?
Yes, sir.
So that I'll write at the end what this is. As of
Okay,
now,
sir.
we are working with delta.
Okay, sir.
Okay. So now, so this would be, so now I can write this q. So let's say now this is q1 and this is q2, let's say. So these are partitions. So q1 I'm defining it as w1, w2. So these are partitions. w1 less than w2, wm. These are the points. Okay, so these are the points. I know that the length. So here the property is that the length of w or wk plus 1 minus wk is equal to delta by m. This is the gap what we are choosing, and q2 is any other points. Okay, and then q is just union of this q1 and q2. So this is the partition of the interval 0 1. Okay, now the way I have said here, so I'll just write it. So this is like, so this ufq I can write it as summation. So first I'll focus on q1. Okay, or let's say in terms of w1. So supremum of f on okay, so I think I have not written properly, because what I'm saying is it's not like that z1 and z2 I'll take as a one interval. So it's like 0 z1 z2 and whatever points are in between. Okay, so I'm not writing it precisely, but so maybe how should I write? Say removing each of the subintervals. So like it's like we are partitioning this 0 w1. Okay, we are partitioning this also. Okay, so let me figure it. It's easy to understand, but so see what I'm saying, that I have this w1 now. So you can forget about y1 y2 as of now. So we have got one kind of partition. So these points are again a partition of this. Okay, so it may not include this end point, but still, except that it's a partition of those points. Now for the rest of the point, I'll choose a partition which is given by z0 z1. Okay, so I'm partitioning in this interval, I'm partitioning this interval, I'm partitioning this, or whatever comes in wk to wk plus 1.
Okay, sir.
I hope it's easy to understand. Okay.
So basically you are enclosing those points in, sir, some different intervals, and those points in some different intervals.
Exactly. So basically what I'm trying to say, let me draw proper photo. So the thing is that I got w1, w2, w3, w4 till wm minus 1 and wm. So I've got some partition, and maybe 0 1 might not be included in this. Okay, so what I'm saying, that I'll construct another partition of these intervals, 0 to w1, w to w3, w3 to w4, and so on.
Yes, sir.
Okay, this is what I'm saying. Now here I will deal separately, because I mean sorry, what I'm saying. So
yes, sir, this is fine, sir.
Yeah, I don't know how to write it. So the main point is that I'll focus on this separately, and for the rest of the points, supremum of f, okay, whatever the interval is, and with multiplied by the length of interval. Okay, that will not anyway counted. So the supremum in each of these intervals, so this here I know that this is less than equal to 1, so this I can say this is less than equal to this wk plus 1 minus wk.
Sir,
let me write it here, just a second.
Sir, you should, sir.
Just a second. So k is from, let me write this 1, sorry, 0,
0 to
1, 1 to m minus 1, right? Okay, because if you want, you can start with w0. Okay, so k from 0 to m minus 1. Now I know that this is equal to, this thing is equal to delta by m, and this is being added m times. So k from 0 to m minus 1, and then this is equal to delta, because this part is easy to get. So here I am using the fact that the interval what I am making is very small, and that is ultimately giving me that this summation is small. Okay, now we have to think of the other part where the function is very small. Okay, now for that what I'm so for that is the set q2. I mean this is summation over this q2. Okay, so if we look at the suprema of the function in these kind of subintervals, okay, okay, so I think we just need to care about these two. Here we can forget, right? So here you don't need to consider these points. Okay, so you just need to care about these intervals, right? We know that these, okay, so the way I have drawn the figure, it looks a bit absurd, because what I'm saying that these intervals are, these points are very close to each other. So w1 is very close to w2, w2 is very close to w3, and so on. So it will somewhere end here, right? They are very close and finite. Okay, no. Okay, well, anyway, uh,
Sir, we should care about those intervals, sir.
I think I messed up. Just a second. Let me write it again. Sorry about this. So this was my y1, y2.
Sir, we should not care about q2, sir. We should care about q1, sir.
Exactly. So that is already handled, right? q1 is handled.
Yes, sir.
q2 is
Yes.
going to give you epsilon. That is true. But I'm just trying to explain how this q1 and q2 looks. That's all. Okay, so this is ym. So from here I constructed this w1. So these points, I think it's better to write it roughly. Naming it is creating problem. So these are the points that I'm considering. Okay, so these subintervals correspond to this q1. Okay, so this orange one are q1 basically. These are the corresponding to q1, and for the other points, so let's say this is 0 1, and for the other points we will just concentrate on. So let me use some other color.
सर फिर ये बीच में y3 y1 भी तो आ जाएंगे ना सर?
No, you just forget about this y1 y2. y1 y2 we don't have to worry about. So
सर ये जो पॉइंट्स हैं इनको सर इंक्लोज करने के लिए हम ऐसे सर सब इंटरवल्स ले सकते हैं ना जो y1 y2 y3.
sorry
सर ये y1 y2 y3 जो है हम ऐसे सर सब इंटरवल्स सर कंसीडर कर सकते हैं ना जहाँ पर सर वो डेल्टा 1/डेल्टा से वो q बड़ा है सर. हमें सर उसको अलग कर सकते हैं जहाँ पर सर p/q ऐसा है जहाँ पर q 1/डेल्टा से सर बड़ा है.
हाँ, so those are the points यहाँ पे, like these are the areas जहाँ पे the function is smaller.
सर z1 z2 z3 टाइप के सर सब इंटरवल्स हम बना लें, उनको y3 उनके बीच में ना हो सर, ऐसे बना ले सर सब इंटरवल्स.
Exactly, वही, that's what I'm saying. So these are corresponding to q1. Again I'm saying the same thing, and these are the rest of the parts where 1/q is very small. So here we are, these parts, if you partition these parts, these are corresponding to this q2. That's all. So here you have to partition it, whatever partition you choose of these sub intervals. Okay, and then you are done. So here this q2, this supremum, so this is going to be less than delta, and this summation q2 over lik, I can make it less than b minus a. Okay, so ultimately what I get is ufq, if I take this is less than equal to, so this will give me delta by m times m, and this is giving me delta by b minus a. Okay, maybe let's write it delta 1 and delta 2. Okay, anyway we can choose delta to be minimum of those two. So this is what we get. Now the question is what is delta? So this is equal to delta 1 plus b minus a. Okay, so now our goal is to make this less than epsilon. This is possible if I define my delta to be epsilon by 1 plus b minus a. Okay, or you can take 2 as well if you want. So this would be epsilon by 2. Okay, and this is less than epsilon. Okay, so this would be the choice of delta that you can make. Okay, so this is a bit clumsily written, so you better understand this picture. Okay, is this clear?
Yes, sir.
Okay, so let's go to the next problem. Next problem. Okay, so this is the, okay, so again this is similar to what we have done in one, so I'll not do it, I'll just write it. Yeah,
सर ये जो W1 W2 WK वाले सर इंटरवल्स थे, तो सर वहां पर हमें सर केसेस बनाने पड़ेंगे ना सर?
कहाँ पे? आई एम नॉट गिविंग नेम टू एनीथिंग. ठीक है, दिस Q1 इज, हाँ दिस Q1 इज W0 W1. हाँ हाँ
सर ये जो WK प्लस 1 माइनस WK है सर, तो यहाँ पर ये हमने ऐसे सब इंटरवल्स कंसीडर किए हैं जहाँ पर जो 1/Q है वो लेस देन है ना?
हाँ करेक्ट. हाँ
1/Q लेस देन डेल्टा.
no 1/Q is greater than delta in this part.
हाँ 1/Q, सॉरी 1/Q इज ग्रेटर देन डेल्टा.
करेक्ट. हाँ
तो सर यहाँ पर जो पॉइंट होंगे वो या तो सर रैशनल होंगे या तो इरेशनल हो सकते हैं सर.
करेक्ट. हाँ
तो सर जब इरेशनल होंगे तो वहां पर तो वो 0 हो जाएगा, तो वो लेस देन सर डेल्टा बाई एम हो जाएगा.
ना
अगर वो नहीं सर, मैं मैक्सिमम की बात कर रहा हूँ इन जगह पे सर.
हाँ
मैक्सिमम सर.
हाँ
तो अगर सर वो इरेशनल है,
हाँ
इरेशनल है तो सर वहां पर वो 0 हो जाएगा फंक्शन की वैल्यू सर.
करेक्ट.
ऐसे हमने डिफाइन किया. यदि वो सर रैशनल सॉरी इरेशनल है तो 0 हो जाएगी. इफ रैशनल टाइप है तो सर वहां पर जो Q ग्रेटर देन डेल्टा
ना सी व्हेन यू आर टॉकिंग अबाउट सुप्रीमम एंड इन्फीमम, वी आर लुकिंग एट दिस काइंड ऑफ इंटरवल. इस इंटरवल में वी आर टॉकिंग. सो व्हेनेवर यू आर टॉकिंग अबाउट सुप्रीमम, इट इज नॉट गोइंग टू बी 0.
नो हाँ सर, नहीं हो सकता 0 ना, वही मैं बता रहा हूँ. क्योंकि वहां पर रैशनल पॉइंट्स भी तो होंगे ना सर. तो रैशनल में सर वो बड़े हो जाएंगे, मतलब उससे 0 से. तो उसको हम लेस देन सर उससे बना सकते हैं सर.
ना वी आर यूजिंग दिस फैक्ट कि f इज ऑलवेज लेस देन इक्वल टू 1. वी आर नॉट यूजिंग द फैक्ट दैट 1/QK इज ग्रेटर देन डेल्टा. ये हम लोग नहीं यूज कर रहे हैं. ये वी आर यूजिंग इन द सेकंड केस.
ओके सर.
यहाँ पे वी आर यूजिंग द स्मॉलनेस ऑफ दिस सब इंटरवल्स कि these are very small. So there are two parts here. We are using the fact that this supremum is very small. Here we are using the fact that these sub intervals are very small.
Yes sir, intervals are थोड़ा सर.
So okay, let me repeat again. So it might look complicated, but it's easy. Okay, so what we did is we found this YKs, okay, where the function is taking, so YK was the rational PK by QK, where the function f of YK is 1 by QK. This is greater than delta. So what we did कि इसके like in the neighborhood of this YK we considered 2 points which are very small, I mean which are very close. So we named it at W0, W1, W2 and so on. In this part we use the fact that this is very small and hence this quantity we made it small.
Yes sir, yes.
Okay. Here we use the fact that in the rest of the part the function is very small and hence this quantity is going to be very small.
Okay.
That's all. Okay, so this is the next question. Okay, so this is similar to the previous one what we discussed in the first part, so I'm not going to do it. You can try it by yourself. Let's move to the next problem. Okay, so this is
Sir, integration of this form function is zero, na? In closed interval zero.
yeah, because LFP we saw that this LFP
Yes,
is
it's
going to be
zero.
0, right?
Yes, yes.
So it's also like if you know the measure theory, you know that the function is 0 almost everywhere, right?
Yes, sir.
So that okay, so that is about Lebesgue integral, but still that will be equal to the Riemann integration. The value when it's Riemann integrable, the both the integral are same, right? Okay,
Yes.
anyway, yeah. So this is it. So we are leaving this. So let's look at this function f. Okay, f is defined from 0 1 to r, and this is defined as fx will be equal to 1 by n if your x is lying between 1 by n plus 1 to 1 by n, and this is 0 if x is equal to 0. Okay, so again you have to do the same thing, check integrability. Okay. So if you have mentioned, let me write here that integration value would be 0 just to be safe. So this shows f is Riemann integrable and since LFP is equal to 0, so let me see, this was UFQ minus LFQ. So LFP is equal to 0 for all partition P. This implies that integral over 0 1 fixed dx is equal to 0. So now again here you have to check integrability and find the integrable value and find. So if it exists, find this 0 1. Again, so maybe what should I do it, or it's doable? Like it's like you are just constant function in each of the subintervals, right? So you can clearly see. Maybe if you want, I can write it. So L F P if you calculate. Okay, so P, let's say again the same partition. P is equal to 0 x0 x1 xn equal to 1. I'll calculate LFP. Okay, so LFP would be just k from 0 to n minus 1 supremum of the function fx. So this would be from k by n to k plus 1 by how should I write it, or maybe you just focus on, let's directly use it. You can directly do this fx dx. I'm just breaking it into 1 by n plus 1 to 1 by n.
Sir,
n from, yeah,
ये फंक्शन सब कहाँ कहाँ पर डिसकंटिन्यूअस है? Sir, it is discontinuous at 1 by
at
n.
each of the this thing 1 by k,
By,
right?
yes,
So
sir.
this function, write it. Okay, so let me write it here itself.
Point of
It's
discontinuities
clear,
are
like f is
counted.
constant in each of this interval, right? So this is how the graph
Yes.
looks. So this is 1 by 2, this is 1 by 3. So in this interval 1 by 2 to 1, I know that the function is taking the value 1. Here it is taking the value half. Here it will be taking
Kinds of step function.
right. So this, it's not step, but okay, you can see in this way. So this is how this function looks. So integration also you can break it into this kind of thing, right? F of x dx, and now this is n from 1 to infinity. directly using it. Now here you know that the function is just constant, so it's integrable in each of these sub intervals.
Sir, we can choose, sir, interval in this survey, sir. You have choose those, sir.
So you're saying
Sir, the
proof for
process
what?
you have used, we can, sir, always, sir, uh,
No,
we
you
can
are saying
always
proof
find
for what? Proof for what?
proof of this, sir, theorem if f has, sir, countably many
Okay, okay,
discontinuous,
okay, okay, okay.
then
Okay, I was
the
saying
function
something
is
else.
Riemann. So we can use this process there.
Correct. In the
Yes,
same way, so here I choose delta by m. So the only change would be here instead of delta by m, you'll have to state delta by 2m, something like
2k.
this,
Yes, sir, 2.
so that it
Yes,
becomes summable. That's all.
yes, yes.
Yeah. Okay. So we know f is Riemann integrable. This we already know. Okay. Now for the function to be this, you want to say 0, 1. So now I can split it into this subintervals n from 1 to infinity. This f 1 by n plus 1 to 1 by n fx dx. I know this function is constant here, n equals 1 to infinity. This function is 1 by n, and this is 1 by n plus 1 minus 1 by n. So this summation n from 1 to infinity 1 by n. This would be n, I think it's wrong, 1 by n plus 1. So this will give you 1 by n into n plus 1. Okay, and you know this summation is finite. Okay, so this is another, or you can actually calculate. I think this.
Sir, you should have
just
taken
calculate.
limit, sir. Na? Why you have written, sir, summation, sir?
What?
So, there should be, sir, limit and tends to infinity, na, sir.
But that will converge to
Because
this series. I mean, it's the same thing.
no, sir, you have taken the summation for, sir, those, sir, partition, na, sir.
No,
And then limit.
now I'm not talking about the partition. So this can be proved. So suppose this is n plus 1 to 1 by n. This quantity is sensible for each n, for all n, right? Now
Yes, sir.
let's say this is from n equals to 1 to, let's say, some capital N. So suppose you are considering just these many points. Okay. Now this I know is an increasing function, right? Because each times I am adding something.
Yes, sir, yes, sir. So got it, sir.
Got
Sir,
it?
वो actually आपने limit ही ले रखी है वो infinity.
Exactly, that's
Yes.
what I'm saying. So this will converge to this n from 1
Yes,
to
sir, yes.
infinity 1 by n plus 1 to 1 by n. So I've written it directly, that's all.
Yes, sir.
Okay, so what is this? So this is what I get. So this function, now this is 1 by n square minus this would be n from 1 to infinity 1 by n 1 by n times 1 by n plus 1, right? So this is summation 1 by n square. This is minus
1 by n minus 1 by n plus.
n plus 1, and this, you know, the value is something pi square by 6.
Yes, sir, yes.
And this is a telescopic series, so this will converge to, so this value will be 1. So here you can
One.
you can prove it, like I think we have discussed this sometimes. This is 1 by
Yes, sir.
k 1 by n minus 1 by n plus 1. So this will give you 1 minus 1 by k plus 1, and then take the limit, you will get 1. Okay. Okay, so we got the value to be of this integral is this. Okay, so we have found this value. Okay, let's go to the next problem. So this is, I think you must be knowing these things, okay, but So f, suppose it's function from ab to r 0 infinity and it's continuous, okay, and you know that this integral a to b, sorry, f is equal to 0, so you have to show f is identically equal to 0. Second question is, what if f is discontinuous? And the third is, what if s is r valued function? So do you know this result?
Sir, if f is continuous and integral is 0, then f must be 0 at those points where f is continuous.
True.
Yes,
But here
from
I'm
there we can see that
using
f is
just the whole continuous.
Yes, sir.
So you know this proof, should I skip it or should I do it?
Sir, there is one person also, sir. You can ask.
Okay, so let me do it quickly. So suppose f is continuous. So if suppose, if possible, f of x naught is not 0, okay, so that means f of x naught is greater than 0. So by continuity of f, there exists a neighborhood delta greater than 0 such that f of x is greater than 0 for all x belonging to x naught minus delta to x naught plus delta, and this will tell you that x naught plus delta to x naught minus delta, this f is greater than 0. This will tell you f of a to b is strictly greater than 0. Since f is greater than equal to 0, so a to x naught minus delta, so here I went wrong, f and plus this x naught plus delta to b, this f is greater than equal to 0. Okay, so this is a contradiction. So this function has to be identically equal to 0. So this is the only place where we use the continuity of the function. So if it's continuous at any x naught point, then at that point it should be 0. That's what it says. Okay, so here let me write at x naught.
Sir, one term is
Mm-hmm.
sir x naught minus delta to x naught plus delta, sir. So last implication, sir. And
Here you are saying a. Here I am writing a to b.
in bracket term, sir. In bracket term, sir.
So
F
here I
greater
am
than or
saying
equal
a
to
to
0.
x naught minus delta and x naught delta plus f b. Now I am
This
saying
will
that
imply,
this is, I know this is greater than 0. Here I am saying these are greater than equal to 0. So the whole summation would be strictly greater than 0.
no, sir. You have written since f is greater than or equal to 0. So this will imply integral a to b f greater than or equal to 0. This cannot be said.
Where are you saying? So this part you are saying?
Sir, if f is greater than or equal to 0, then can we say that integral of f is greater than or equal to 0 in that interval?
Why not? If f is greater than equal to 0, then I know that integral on, so suppose it's greater than 0 on some interval I, if we take integration I, f, this is greater than equal to 0, right?
Yes, sir. So, sir, what you have, sir, proved? Sir, if we know that this integral is greater than 0,
no, so see, f greater than equal to 0 will tell you that integral f is greater than equal to 0 on ab, but here I am saying that it is strictly greater than 0, and that's why I am getting a contradiction. If it is this, then I cannot get a contradiction, right?
okay, sir.
So here I am saying that this integration is strictly greater than 0, and why this? Okay, so I think I should elaborate it. Okay, so say this is what I have, a to b f. Okay, this I can write it as a to x naught minus delta plus x naught minus delta to x naught plus delta f, and this is x naught plus delta to b f. This I can write. I know that this and these are greater than equal to 0. This is where I am using the fact that f greater than equal to implies this is greater than equal to 0. But what I have got from here is that this is a strictly greater than 0. So the whole term is a strictly greater than 0.
Yes, sir. Yes, sir.
That's all I am saying.
Okay, sir.
Okay, I think I should have written it somewhere. Anyway, okay, so let me keep it here itself. Okay, fine. I thought you know the proof, that's why I just skipped the details. Okay, what about the second part?
Sir, I know this proof indirect, sir.
Okay, okay. What proof you know?
Sir, by just. Okay, sir, I have notes. I can.
Oh, no, 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 it's fine, it's fine. Okay, I thought you are saying you want to say the proof. Okay, anyway. So what about the second part? Like, what if f is discontinuous? Can you still conclude?
No, sir.
No. Can you give just example? So just take 0 everywhere, let's say, and at one point you just take 1. So this function integration is going to be
Form
0.
function, sir.
Thumb function, like just take the general function. No need to, like you don't have to go to thumb function. This, but f is non-zero, right? This function you can see.
So we have discussed that function, sir.
Yeah, but I am saying this is simpler one, right? Thumb
Okay.
function is already there. So what about the third one? So see, here we have used the fact that f is greater than equal to 0. Otherwise we could not conclude this. So what if I remove this condition?
This we cannot then conclude, sir.
So can you give some example? So you can think of this function, any function like you want. So this kind of symmetric. So whatever area is above, let's say what the same area is below. So say this is A, this is B, let's take this as midpoint. Okay, and let's say this height is same as this height. Okay, the picture might not look good, but here you can see that the integration would be 0, but f is not 0. Okay, or anyway you can use this as well. So just take this function what I have given above, that will also work, right? So 0 minus 1, 0 1, 0. So integration of f is 0. Okay, but here you have to take continuity. So I say it is real valued continuous function. Then that example, then this example would work. Okay. Yeah. Okay, let's go to the next problem.
Okay. Sir, if replace this condition, integral fx is equal to integral f of x whole square is equal to 0, then in that case we can say that.
Yeah, then that means that you reduces to case 1, right? When you say f square, that is the case 1. The g is equal to f square is case 1, right?
Yes, sir.
So suppose f ab to r. Okay, so this is a. So f square integrable implies f integrable mod f integrable implies f integrable. So is this true?
I think it should not be true.
Yeah, it is not true. So you just take this function, right? 1 x belong to the usual thing what we do, 0 1 and minus 1 when x belong to q complement intersection 0 1, let's say. Then you can clearly see that this function is not integrable, right? So f is not integrable, not Riemann integrable. But f square is and mod f, these are just constant function, right? So this implies this mod f okay. So this is the problem 7th. The problem is like this. So suppose f from AB to R and G is from CD to R. This, let's say these two are integrable function. Okay, and then suppose f of AB is contained in CD. So this tells you that
Position is well
G
defined.
composition F makes sense. Now the question is, when can is when I can so when the yes, question is G composed F integrable? Okay, so in general, like as you can think, it's not true. So can you think of some example such that this function is this f and g are integrable, but the composition when you take it becomes not integrable? Can you think of some function? And then we'll go to the actual. So let's say this is A and B. I'll say what it is.
Sir, 1 minus 1 minus 1 1 type functions, but they are not integrable.
Okay, so it's not. So let's take f. So see, the thing is, what should be the example? So
1 1
so
0,
see
sir.
G.
We define, sir, Thom function, sir.
F, let's take f to be Thom function. Okay, so let me write the definition. So 0 when x belongs to Q complement intersection 0 1 union 0. This is 1 by Q if x belongs to Q intersection 0 1, or sorry, x equals to P by Q. Okay, so now you can clearly see. So this we know that f is integrable. Now thing is, if I so this you can see that the range of f, okay, sorry, that the f of 0 1 is always sitting inside 0 comma 1, right? So I have to define a function g on 0 1 which
0
is
1,
integrable.
sir.
Sorry,
0 1.
so did I write something wrong?
No, no, sir.
Okay,
I'm telling you the function, sir.
okay, 0 1. When x, let's say 0 to 1, let me see, and 1, suppose if I define it in this way, okay, then 0 G compose F. No, let me say this is x equal to 0 and then x belong to x belong to 0 1. Okay, let me see. So G composed F. So when x is equal to 0 or rational,
0.
let's take, then it won't be integrable. So let's say x equal to, just a second, so if I take 0, f will be 0 1 rationals, irrationals and 0, right? So if I take x to be rational, Q irrationals 0 1 union 0, then this function would be 0. Okay, and yeah, now I think it's okay. And if I take x to be other than this, so if x is equal to p by q, then I know fx is going to be a non-zero number lying between 0 and 1, so the function value would be 1, and in this case this composition won't be integrable. This G composed f is not integrable. Okay, so now the thing is, how can we say that this is in what situation this composition will also become integrable? And the condition is, suppose that this function g is continuous. That is enough. Okay, so g cd to r is continuous, then g composed f is integrable. Okay, and so we'll prove this first and then we'll go to that question. So clearly that x 1 by 3 is a continuous function. Okay, but just a second. Okay, we'll come to that later on. First say, let's say g is continuous, then can I conclude g of composed f is integrable? Okay, so now again, so what do we have? We have that f and g are integrable. So g is continuous and this compact means that g is uniformly continuous. So we have some uniform gap. Okay, using that we have to conclude g composed f is integrable. So for again we'll do the same thing, that we'll try to look at this thing, p minus l g composed f p. Okay, our goal would be to make it less than epsilon. Okay, so let us first choose let.
Sir, are there any necessary conditions for integrability, sir?
So these are equivalent conditions, right? It's necessary.
Yes, these are equivalent, but is there any necessary conditions for Riemann integrability, sir?
So integrability implies that the function should be bounded. That is one of the necessary condition. That if your function is Riemann integrable, then the function has to be bounded. Okay,
sir,
so
we assume, no, sir. We assume that
actually,
function
okay,
is
so
bounded.
there are two ways to define Riemann integration. Yeah. So how should I say? So if you go by Darbox sum, then you have to assume f is Riemann integrable. But if you define it in this way, that integral f summation f of si, let's say ti, I mean xk plus 1 to xk, where this is sk. So sk is any point this one. So this is another way of defining Riemann sum. Then so if you have this kind of, if you start with this definition, then you will have to, so from here you can derive f is bounded. And so this is one thing, but for Darbox sum, just necessary condition. So this is a necessary condition, but you are just looking for just for necessary condition. I don't know. So this obviously is a necessary condition. I don't know what you are asking for.
Only type of condition, no, sir.
Sorry.
These are equivalent conditions, sir.
Equivalent means that it's necessary.
Yes, sir, I know that, sir.
So do you want some specific thing? Like
yes, sir, only necessary conditions. From there, sir, by contradiction, we can conclude the function is not, sir, Riemann integrable, sir. Sir, I know sufficient conditions, sir, if continuous and if monotonic and uniform ellipsis, then implies. But I don't know, sir, about necessary conditions.
If you start with Darbox sum, I don't know. Yeah, this you can say, right? I mean, okay, so if you just want for integrability, that's what I was saying, that if f is integrable, then the point of discontinuity, okay, but it will be in terms of measure, but no, but that would be not applicable over here. Like f is Riemann integrable implies that the points where it is discontinuous is of some non-zero size, is of zero size. So if you get a set whose measure is positive, then you can say that this function cannot be Riemann integrable, and that kind of thing.
Okay.
It works. So that is one of the condition that one can use. No, any I can also not think of any other conditions at this point. What could be? Okay, so now let's come to this problem.
So sir, to prove the function is not Riemann integrable, the above function, we should have to consider, sir, some partition, sir.
Okay, you want to say this is not integrable, you want to show this?
Yes, sir.
This is just easy, right? So you just calculate UFP and LFP.
Yes, sir. Yes, sir.
I mean that's how you
That
get
is
it.
what I am asking, sir. If we have a necessary condition, and if we are able to show that the condition is not satisfied, then this is not integrable. That is why I'm asking about the, sir, necessary conditions.
Yeah, I understand why you are asking necessary condition, but for this function it's very easy to conclude. You just
Okay,
calculate
sir.
LFP and UFP. You get that one of
Zero,
them is
zero
0,
and one, sir.
one
Na?
is 1, right? So it can never
Zero and
be.
one.
Yeah.
Yes, sir.
Okay, so I thought this is immediate, that's why I didn't mention.
Yes, sir. This is immediate, but sir, I for
Oh,
others,
okay,
sir,
okay. You were
problem.
asking in general.
Yes, sir.
Okay. That I don't know. That one thing is there that using the point of discontinuity, you can say something. That is one of the condition that you have. Okay, but other than that, I don't know.
Sir, for that the integral should be zero, sir, na?
For which?
Sir, for if a function integral of a function is zero and it is continuous.
Then the function has to be 0 if it is non-negative.
Yes, sir.
So okay, are you talking about G?
No, no, sir. I was talking about, sir, the necessary conditions.
But that is different. That is not necessary condition. It's something else.
Yes, sir. Sir, you can discuss
Okay.
in other session.
Sure. Okay, so we want to prove that this thing is very close. Okay, so let us try to write this definition. What we'll get. So this will be some supremum. Okay, so again, so I'm denoting it. Okay, but it would be chaos. Okay, so let me write G of fx xk to xk plus 1 minus supremum xk to xk plus 1 G composed infimum, and then xk plus 1 minus xk. Okay, so now, so I have two things. So let's say this is star. So what I have in hand is, the first thing is I know that G is continuous. So that is uniformly continuous, let's say. So this will tell me that if you take Gx minus Gy, so for any epsilon, there exists delta greater than 0. Okay, so for all xy belonging to this CD. Okay, so this is what we have. So let's say this is 1. The other thing what we have is, so see, we have to make this less than epsilon. So if I can show that these, okay, I think the way I have written, okay, we'll come to that, but somehow I want to make this less than epsilon, and I know that the function f is also integrable. Okay, so using that, I'll have to conclude that this is also less than epsilon. So the point is that I need some partition, right? So this I am starting with any partition. Now So for since this function f is integrable, so for epsilon, okay, so this is not this, okay, so let me write this is some epsilon tilde there exists, so I'll choose this epsilon tilde maybe later on. There exists some partition pf such that u f comma pf minus lf comma pf is less than epsilon or epsilon tilde. Okay, so let's say this is 2. So I have these two conditions in my hand, and I want to prove that this will be very small. Okay, so now I can deal with this pf. So I should have written it later on, so let me cut it off from here. Okay, let me first write these two things, then I'll start with this pf. Okay, so now I'm starting this, so this p is, I'm starting with this pf. Okay. Okay, so if you want to rewrite this, what I have is that this is telling me that this supremum, okay, let me write this mk just to be simplicity. Okay, this is less than epsilon tilde. K from 0 to n minus 1. Now over here I know that G is uniformly continuous. So if I take this, if I restrict my study on this set, let's say, okay, suppose I'm just restricting my study on this one. So what I know is that G, so this f will be attaining its, okay, f is not given to be continuous, but what I know is that the supremum mk and this mk, okay, this I don't know that this is small or not. Okay, so if I can somehow say, how should I say this, just a second. So this supremum, so I have to somehow use this fact and the continuity. Now I can use, okay, let me think. So I can use continuity when I can say that fx and fy, okay, I think I'll have to further refine the partition. If I can say that this is small,
sir, f is uniformly continuous, no?
yeah, f is not uniformly continuous, G is given to be uniform. So this I can make it less than epsilon. I mean, I can make it very small when my this function is small. So if I choose my partition, okay, if I refine my partition further, then I can make this one less than, I mean, very small, okay, which will imply that this is also very small. Okay, so let me write it in this way. So I have to make sure that this becomes very small, I mean less than delta. That this will force me that this is small, and this will force me that this is small. Okay, so I think I'll have to consider refinement probably. So consider P to be refinement of PF such that this MK, I mean supremum of F, or such that Fx minus Fy, Fx minus Fy, this modulus would be less than delta for all xy belonging to this yk to yk plus 1. let me see, I think this should work. So if this is there, then what can I say? So from here I will get that the difference of supremum of fx and infimum of fx over this, sorry, yk to yk plus 1, this difference is always going to be less than delta, right? Because the maximum what the function difference is delta, so this supremum is always going to be this. Okay, and then okay, but there is a but from here, yeah. Okay, so I think this is enough, I don't need this. So from here only what I can say, that if I try to study this supremum of xk to x, sorry, yk to yk plus 1 of this g of fx minus infimum of yk to yk plus 1 g of fx, if I look at this difference, I know that the function on this interval are close as delta. So this g, if you remove this, okay, so at first you can remove this infimum. So let me write one more line. This copy. Yeah. So what I'm saying, let's forget about this. So I can say that g of fy minus g of fx, this is always going to be less than epsilon. Okay, epsilon. Okay, so here also, okay, so let me say this is epsilon 1, this is epsilon 1, and let me say this is epsilon 2. We'll choose it later on in terms of epsilon. Okay, so this is less than epsilon 2 by 1. Okay, and now I can say that the supremum, this gap is also going to be less than epsilon 2, and this will tell me that if I look at this summation u g composed f on this refinement p, okay, but I'm missing something probably, just a second, I will see, L g composed f p, okay, then this would be, this gap I know is less than epsilon 2, okay, just something, okay, let me see, epsilon 2, and then this is b minus a. But I'm just amazed about this fact that where I'm using that the f is integrable. Well, otherwise I don't need this refinement also. Okay, yeah, how can I say this line? Okay, so you understood. So the goal is clear, that if I can find a partition where this function is very close, then I have all the things are follows up. Okay, but this you cannot guarantee, right? And here you will, okay, here you will use this fact. Okay, so I think I just wrote it in a wrong way probably. Okay, so I think what can be written is okay, so the thing is, if, so let me write it in this way, so this is wrong, so let me just slide it here a bit. So if, I mean, so let's work on this pf itself. So suppose on this interval xk to xk plus 1, okay, if my function this f is satisfying this property, that this mk minus mk, if this is less than delta, then I'm done, right? So this would imply all these things. Okay, if this is true. Now the thing is, when this is not true, how to deal with it? So this is one case maybe. Okay, so just the thing, yeah. Let me cut this off, then it follows, right? So there will be. So if I know that the maximum and minimum value is less than delta, then I am done. Now the thing is, what if it is not true? So suppose it cannot be always true, right? So if so let's say this is case 1 and this case 2 probably. Let me think. Case 2 would be that on xk to xk plus 1, this mk minus mk is greater than equal to delta. Okay, then what will you do? Now you know that this thing is very small, so somehow you have to say that such scenario cannot be possible for infinitely. Okay, sorry, we are not anyway dealing with infinite thing, but somehow from here I have to reduce it to case 1, right? Then we are done. Or okay, no, what we can do is, yeah, okay, so here again, like what we did for the thumb function, okay, the same argument can be used. So let me write it in a. Okay, so then I can combine these two cases. Yeah, okay, so I think, so let me just say, okay, so what will happen if my, on this case, mk minus mk is less than delta? Okay, so what I'll do is, now, so these are the two cases. Now let's look at this thing, okay, star. So what I can say that u at the argument what I wrote will be used. So let me just paste it here. Okay, that should be. So again, I can split it into two parts. So this summation pf, sorry, L, this I can split in two parts. The one part would be where the function is very small. Okay, so I think, sorry, I should not have. So I think I'll just write this conclusion, whatever I have, these two lines. Okay. So when my partitions are satisfying this property that the function value is very small in those partitions, then I know that this is less than epsilon 2 from here. Okay, so what I can say is, and for the other part what I know is, okay, so in this case what I can do is, so again, like before, this is less than equal to, suppose I'll split it into two parts. So like case 1 corresponding to that case, I have this is less than epsilon 2, strictly less than. Okay, and there that I have less than epsilon, this is xk plus 1 minus xk. Now for the case 2, what I have is, this is greater than equal to delta, but I also have this g is uniformly, so g is somewhere which is bounded function. So now I can say that this whole quantity is bounded by something. Okay, so I can say this is less than c. So maybe I can say, so I'm assuming, okay, so here only let me write. So g, I know that g is continuous on compact interval, so I know that g is bounded by m. So let's say here it will be 2m, right, because of these two things. And then I have this summation xk. Okay, now what I have is, okay, somehow I'll have to use this to conclude that this is also small. let me see. So I've used this over here. Okay, so this I can make it, obviously this is less than this. I can say this is b minus a, and this would be some finite sum, so this would be some constant, let's say k1 times epsilon 2. So this I can make it small, that this is easy to do. Now in this part, what we can do is, I have this information. Somehow I'll have to somehow include this mk plus 1, mk minus mk. Okay, so let me write this as like that. Sorry. So here what I can add and like divide and sub this I can do probably. So let me write it in this fashion. This I can write it as mk minus mk and then mk minus mk. Okay, suppose I write it, then from here I got, okay, but for mk I'll have to find the bound. So then I know that this quantity, so somehow this I can make it out, this I can bring it outside summation. Okay, now somehow if I bound this function, this quantity, then but let me see how can I bound it. So I know that this mk is less than equal to some constant m.
Sir.
This, yeah.
Sir, mk and small capital mk and small mk are the, sir, maximum and minimum values, na sir? On that.
Correct.
Formally continuous, there will be some, sir, point where they will function will assume the values, sir, mk and mk.
No. F is not given to be continuous. That is about G. F is just given to be integrable. Okay. That's all information you have. Okay. But what one can do is,
sir, but 2m you have replaced for gx, na sir?
This I have replaced for gx. Now, okay, so let me explain what I have done. So I have split it into two parts. One part, like just as in Thom function, I have used one part, this fact, that where the this is small. Oh, okay, I can use this, right? So I have this fact. Okay, so let me explain it again, or let me first write it, then I'll explain it. So this, I have this mk minus mk is greater than equal to delta. So this I can say this is 1 by delta. So this is 2m by delta, and then case 2 thing, and then this is less than epsilon 1, right? From 3. So this is epsilon 2. This is by 3. Yeah, now it's done. Okay, so let me explain again properly. So see, we have two things that has been given to us. The first thing is that G is given to be uniform continuous. Okay, G is continuous and f is just an integrable function, nothing information about f. Okay, so what we did is that I know that I have to prove that this for some partition this is very small. Okay, this is what our aim is. So I chose some epsilon, small number. Now I know that G is continuous, so G is uniformly continuous because this is compact set. So I have this thing that, okay, where did I, sorry, this is G. Okay, so this I know by definition of uniform continuity, that for any epsilon 1, okay, there exists a delta such that this is very small if x minus y is less than delta. Okay, this is by the definition. Okay, second thing is that I know f is integrable, so I have a partition for which this thing happen. Again, you have some epsilon 2. Okay, now I would like to see for this partition, okay, how this u and l behave, like what is the difference. So So when I start it off, I'll get this, just that by definition I am having this quantity, suprema of this. Now see, one case, suppose these fx and f, I mean, okay, so here it's x and x, but suppose in this interval xk and xk plus 1, I have that this value f, and for any 2 points in this sub interval I have this fx and fy are less than delta, then I can say that g of that minus g of that will be also less than epsilon 1 or 2, whatever I have chosen, epsilon 1. Okay, so that's what I have written, that suppose on sum this xk to xk plus 1, this function, the maximum value and the minimum value is less than delta. That means that each of the point it is less than delta only, because the maximum and minimum are less than delta. So if you take the modulus of values at any 2 points, then it is going to be less than delta. This is what I have written here. Okay, so this is xk. Okay, so I have that this function is, this modulus is less than delta, and because of uniform continuity I have this, and now once I have this, I know that the supremum minus infimum is always going to be less than this, because it is true for any x and y in this intervals. Okay, so this gives me that this term is small, correct? So when this is happening, case 1, then I know this is small, and hence I can say this whole summation would be small. So that's why I've done, I've split it in case 1 and case 2. Case 2 would be just the negative of this, that mk minus mk is greater than equal to delta. So there are two cases. So for case
Sir,
1, yeah.
Sir, then we are dealing with this F composite G, sir.
G composed F,
Yes, sir, G composite. So, sir, why we cannot use this uniform continuity directly here, sir? Why do we need, sir, Riemann integrability of F, sir?
So what I wrote
Can we
earlier, you
not
are saying
directly
that
use here,
what I
sir?
wrote earlier, are you saying that?
Yes, sir.
So I said that any partition if I take, that partition has to be less than delta. So
Sir,
so
any
see, I can
function is
choose.
Riemann integrable, sir, na, sir?
Uh-huh.
Any uniform continuous function is Riemann integrable
Uh-huh.
over. So, the range of F is, sir, domain of, sir, G,
Huh.
and G is, sir, uniformly continuous. So F composite G is, sir, Riemann integrable, sir. Can
Without
we not?
integrability of f.
Yes, sir.
How you are saying?
Sir, because sir, range of F is domain of, sir, G, sir, and G is, sir, uniformly continuous.
So what?
So F composite G is, sir,
Uniformly continuous.
yes, sir.
How can you say that? No, that's not true, right? You are saying very strong statement. You are saying f is any function, you are saying, okay, and then just because G is uniformly continuous, you are saying that G composed f is uniformly continuous. Okay, so tell me that G composed f, is it continuous also?
Yes, sir.
That's not true. Okay.
Yes, sir. Yes, sir. Yes, sir. Got it.
Yeah, so what I am saying that, so there will be two cases where in one case I know that this size I can assume it is small, then we have everything, then it's very fine. The second case would be where this is not less than delta, it is greater than delta. In that case I will use this fact. Okay, and what I did is I just write epsilon 2, okay, sorry, this is just I bounded this function, I know this is a bounded quantity, so I bounded it by 2m just because gx is bounded, and then this thing was there. Now I multiplied and divided it by this.
Yes, sir. Now it is clear, sir.
This is greater than equal to delta, so I have this lower bound, upper bound, and hence it's done. So now this you can choose epsilon 2 and epsilon 1 accordingly. Okay, so that's how you can do it. If you want, you can choose epsilon 2 to be epsilon by 2 k1, and epsilon, sorry, this is epsilon 2, then this is epsilon 1. So this is epsilon 2, epsilon 1 you can choose it as epsilon by 4 m delta, then you will get u g composed f pf minus l g composed f pf is less than epsilon. Okay, so this proves that g composed f is Riemann integrable. Okay.
Sir, can we replace uniform continuity by this monotonicity, sir?
By
By monotonicity of the function g, sir. If f g is, sir,
no,
monotonic.
I don't think, because that is very strongly being used over here. No, because without uniform continuity, I don't think this can be replaced by monotonicity. Okay, let me see. The example what we give is monotone, right? See, this g function is monotone. Still. Okay, so that's all for today. Okay, so I had few more questions, but anyway, I'll do it in the next session probably.
Okay, sir.
Okay, then see you next week then.